So we'll start at 3:05. Just wait for a couple of minutes. Let's see if someone else joins. I think we should start with this. Someone else joins. I'll just admit them at that time. We have to start. So I welcome you all. So the attendance is quite low today. Yeah, we should quite usually expect towards the end of the course. But anyways, I hope people will watch the live recordings and are joining the other TAs as well. So today's lecture number, live session number 11, where we are going to discuss problems related to microprocessor 8085. So most of the questions are related to where their assembly language code is given, and we are required to find out the contents and other things and delays and so on. And in the next live session, that is the last live session of the course, I think week 12 also deals with the microprocessor 8085. So there we are also going to see questions pertaining to microprocessor 8085. So without further ado, I think we should start. So again, I would like to introduce myself. My name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. I'm the course TA for the course Digital Circuits. It is a NPTEL course taught in the month of from the months of July to October. The course is taught by Professor Shantanu Chattopadhyay, and today we are going to discuss questions pertaining to week 11's material. Before we start, what I would like to do is just give a brief overview of this microprocessor 8085, the architecture of 8085, which is quite important. It will be just a brief overview. We're not going to that much details. I'll just spell out the things what there are and give the brief overview of them. Rest you can always refer to your lecture notes for more details. It's just a brief overview that I would like you guys to show. So so this is a a diagram of for this architecture of 8085. We'll call this microprocessor 8085, right? What this microprocessor 8085 is? It's a 8-bit general purpose microprocessor. Just a second, someone wants to join. So let me just continue where I was. So this is the first thing we are discussing today. Is this the architecture of 8085? What I will do is I will give a brief overview of this microprocessor, and rest you can always refer to your lecture notes. It will just be a brief overview of the things that there are in microprocessor 8085. So microprocessor 8085, it is a 8-bit general purpose microprocessor. Has got these following fundamental units. So we have this ALU, which is the arithmetic logic unit. It is used to perform mathematical operations like addition, multiplication, subtraction, division, decrement, increment. And this ALU is also responsible for the logical operations, bit shifting operations, and other arithmetic operations. So this is your ALU in short. Then we have flag registers. These are here. It is again an 8-bit register that states 0 or 1 depending upon the value stored in the accumulator. Right. Among the 8 bits, only 5 bits are important, the rest 3 are don't care. Then we have the accumulator here, right here, which is a 8-bit register. What this accumulator does, it's used to perform. Sorry, I'm sorry, but someone wants to join, so let me just admit the person. Okay, so let me just start from the. Let me just start again. So sorry about the participant that already had this introduction, but let me just do it again. So what we have here is in this today's live session, we are going to discuss microprocessor 8085 related questions. So before we proceed, I thought I'll just give a brief overview of this microprocessor 8085, in particular the architecture of 8085, which I found was really important. It will just be a brief overview. We'll not go into details. You can always refer to your lecture notes, references for details if you want. So what I said was this microprocessor 8085, it is a 8-bit general purpose microprocessor. It has the following functional units. First of all, it is the arithmetic logic unit, which is the 8-bit register. It's used to perform, arithmetic logic unit. It's used to perform the mathematical operations like addition, multiplication, subtraction, division, and it is also responsible for the logical operations, bit shifting operation, and other arithmetic operations. Then we have the flag register, which is the 8-bit register that shows 0 or 1 depending upon the contents in the accumulator. It has among the 8 bits, 5 bits are only important, other 3 are don't here. Then we have accumulator, which is a 8-bit register. It's used to perform the arithmetic, it's used to perform input output arithmetic and logical operation, and it's connected to ALU. Let's see, it is connected to ALU and the internal data bus. It is the heart of microprocessor because all the arithmetic operations, accumulators 8-bit pin will always be connected with the ALU. Then we have the general purpose registers here. There are 6 general purpose registers. These 6 registers can hold 8-bit values. All of them can hold 8-bit values. These are B, C, D, E, H, and L. And W, Z are reserved registers. As you can see, they are shown the temporary register here. Then we have this program counter, which holds the address value of the memory to the next instruction that is to be executed. So it holds the value of the address, the value that needs to be extracted in the next instruction. Then we have the timing and control unit here. It comes under the CPU section and it controls the flow of data from the CPU to other device. Also, we have the interrupt control here. The 5 interrupt signals are here. And what is this basically interrupt signal? So suppose a program is running and we want other program to be executed. So we request the interrupt, the main program gets stopped and the requested program gets executed, and then the main program is executed again. So there are these 5 interrupt signals. These are trap, RST 5.5, reset 6.5, reset 7.5, and trap. And the order of this priority is trap is greater than reset 7.5 is greater than 6.5 is greater than 5.5 is greater than interrupt. And then we have the data bus, which is a bidirectional data bus and carries data which is to be stored. And we have the address bus, which is unidirectional and carries the location of where data is to be stored. So address data bus carries the data which is to be stored, Address bus, which is the unidirectional, carries the location where data is to be stored. So this was just a brief overview, not going into detail, just showing the things here. Rest, if you want to go deep into this microprocessor 8085, you can always refer this textbook from Gonkar, which I found really interesting, and I used to refer to that book during my bachelor days. Now I think we'll be discussing the questions for today's live session. Just a second, let me just note it down somewhere. And also next week we'll also be discussing this thing, what we call is microprocessor 8085. We'll be discussing that thing again. So now let's start with the first question of today's live session. So it states that how many flags are there in 8085 microprocessor? Can someone tell me how many are there? Oh, let me just tell. There are actually, yeah, 5 flags. But this flag is basically a register which contains 8 bits, right? As I already told you, 3 are don't care, so we don't care about them, and 5 are relevant. So among these 5, we have the 0 flag, the carry flag, the sign flag, the sign flag, the parity flag, and the fifth one is auxiliary carry. So this 0 flag is what should I say is 0. So this 0 flag is 0 when all I think I'm getting confused. It's 0 or 1. I'm not sure about that. But when all the on accumulator, when all the bits of the accumulator are 0, this is I think 1. I think it's 1. 0 flag is then 1. If it's not, then let me just check it. I'll just come back to it. I'm not sure about that. Then we have the sign flag. If the number is after the operation, if the contents of accumulator are positive, it's 0. Otherwise, it's 1. Parity flag, if there are even number of ones, it's 1. If even parity, it's 1. For odd parity, it's 0. Even ones, it's 1, and even odd ones, it's 0. Auxiliary carry is in BCD addition. If during BCD addition there is a carry transfer from D3 to D4, it's 1. And then we have the carry flag, which is when after a arithmetic operation you get the result in more than n bits. Here it's 8, so if you get a result from more than 8 number of bits, this gets to 1. So where is it? This gets to 1 when there is a result of your operation is more than n bits, and this is 0 when it's within n bits. And 0 flag, I think, let me just check. I am getting confused here. After operation 0. Okay. Okay, I think if contents of accumulator are 0, 0 flag is 0. Yeah. If the contents of the accumulator, yeah. If the contents of the accumulator are 0, 0 flag is 0. Otherwise, it's 1. I hope I'm right here. Huh? Can someone correct me regarding the 0 flag? If the contents of accumulator are 0, it's 0. Otherwise, it's 1. Right? Requesting every participants to please turn off their microphones and visuals. So now I think we are ready to go. So the answer to this question was 5. And I can also show the location where are these present. So if we can divide the contents of accumulator like this, 1, 2, 3, 4, 5, 6, 7, 8, and this is your D0, D1, D2, D3, D4, D5, D6, D7. So here is your carry, here is your parity, here is your auxiliary carry, here is your zero flag, and here is your sign flag, right? Now the next question is, I would like you guys to tell me the answer to this. The program counter stores option A address of the current instruction executing by the processor, option B address of the previous instruction executed by the processor, option C address of the next counter to be fetched from the memory, option D none of the above. So what do you think is the correct answer to this? I already in my starting slide I gave this brief overview. I mentioned this. What does this program counter does? It shows the address of what? Yeah, it shows the address of the next instruction to be fetched from the memory. Correct. That is option C. So option C is your right answer. Here is their program counter. Now again, which of the following is not a valid 8085 instruction? You have this LDXB, LDXH, LDXD, and increment M. So which of the following is not a valid instruction? 8085 instruction. Anyone? Can anyone tell me the answer to this question? I see some of you guys have written in the comments. So people are writing D, yeah? Question 3. So I'm asking for question 3. Which of the following instruction is not a valid 8085 instruction? So D. No. So let me just tell you. The correct answer to this question is option B. That is LDAX-H. Because this LDAX takes the input as register pair, either BC or DE. So LDXB is valid, LDXD is valid, and if this is increment M, which is to increase the contents of memory, it's also valid. This LDAX will take your input here as register pair, which are BC or DE, that is LDXB, LDXD. H and N are not registered, it can't take H and N as the instruction. So option 3, question number 3 has the correct option as this LDXH. It takes LDX is the instruction only uses BC and DE register pair. So let me just write down LDAX RP only uses BC and DE register pairs. Then I have this question: which of the following is not affected by the CMP and CI instruction? So CMP is this compare instruction. So CMP is a 1 byte instruction. It compares the data byte in the register or memory with the contents of the accumulator. So what this does, it compares contents of register and memory to accumulator. So if the contents of accumulator A are less than R and M, so if A is less than R M, it says carry flag to it sets the carry flag. So carry flag 1 and 0 flag is reset. This is set and this is reset. If A is equal to the contents of memory or register, it 0 flag is set and carry flag is reset. If A is greater than contents of register memory, the carry flag and the 0 flag are both reset. And when a memory is an operand, the address is simplified by the HLPR. No contents are modified. However, all remaining flags SP auxiliary carry are affected with the result of subtraction. So the only thing that is not affected is this parity flag, this option D. This is not affected by this instruction. Rest all of them are affected. Apart from this, parity flag is not affected by the instruction CMP which basically compares the contents of the register and memory to the accumulator. So if A is less than register and memory, say carry flag is set, 0 flag is reset. A equal to register memory, 0 flag set, carry flag reset. A is greater than register memory, carry flag and 0 flag reset. And when memory is operand, its address is specified by HLPR. No contents are modified. However, all remaining flags are affected according to the result of subtraction. So this flag is not affected by the CMP instruction. Now we have this question, which is to find the total delay produced by the following program. Assume 8085 microprocessor running at 2 MHz clock. So this thing is basically microprocessor. This micro, is a symbol mu. We call this mu is a symbol for micro, and P here stands for processor. So in short, we write this microprocessor is running at 2 MHz clock. So F is 2 megahertz. Now we are given this, what should I say, following program, and we need to find out the total delay produced by the following program. So we have this move immediate. So we have this instruction. We have this instruction move immediate C 0E. So this takes 70 states. Basically, it moves the content 0E to the register C. Then we have this loop thing, DCRC, which is decrement the contents of C, and this takes 40 states. Then we have jump on non-zero. So if the contents of the accumulator are non-zero, it will go back to this loop, jump on to the location, jump on non-zero to location, and this thing takes 10 states for a successful when the condition is met, and 70 states when the condition is not met. So then the loop executes successfully. It takes 10 states. Otherwise, it takes 70 states. Take across. So we'll just find out total t states. So total t states is the loop outside the loop, so we'll call it TOL, and inside the loop we call TIL. That is equal to, now we'll find TIL first. So TIL is basically 0E. So 0E is basically, if you convert it into a decimal, it's 14. So the loop will be executed 14 times. 14 multiplied by the number of states. How many is there? 14. 10 plus 4. So total t states inside the loop is 10 plus 4. 14 multiplied by 14, but I told you when the condition is not met, only 70 states are there. So in the last case, only 70 states will be needed. So it's 14 multiplied by 14 minus 3. So 14 multiplied by 14 is 14 square is 196, multiplied by minus 3 is 193. These are your t states inside, and TUL is simply 7. So TUL is 7. So 193 plus 7 is 200. So total 200 t states it requires. So 200 t states is the total delay. Total program delay is 200, and t will be equal to 1 by f, that is 1 by 2 into 10 to power 6, and you know that your total delay will be equal to 200 into t, that's 1 by 2 into 10 to power 6. So this is 2 1 and this is 200. So this thing is equal to 100 into 10 to power minus 6, and this thing will be equal to 100 microsecond. So option A is the correct answer. So I'll just repeat what I did here. We are giving this program, which is move immediate C, to load the contents of the register 0E, then decrement C, and whenever if the result is non-zero, it will go back to the loop, that is the decrement C. So this will run up to 14 times and it will become zero. So in the last stage, it won't be executed. So this thing will be run 14 times, and in the last case, the condition is not met, and that times only 70 states should be taken. Otherwise, for a successful match, it will take 10 t states. So so inside the loop, decrement takes how many states? A decrement operation takes 4t, and this takes 10t when met and 70 when not met. So inside we have 14 states, assuming that condition is met. So what I did here, I multiplied this 14 times 14 number of times loop will be executed minus 3 when the last condition is not met. So 196 minus 193, so 193 states it will take for that 14 times. And then we have the 70 states from the move immediate operation. So total delay will be 200 t states. And for one time period, it takes 100 microsecond. It takes 0.5 microsecond. So you multiply zero point 0.5 by with 200 and you get 100 microsecond as your total delay. So total delay will be t into number of clock cycles required. So the number of clock cycles are 200 and t is the individual delay. So that is 200 multiplied by 0.5. Any doubts here? Yeah, someone has already done it. You are given this table. I think if you refer to these reference books, these are well found in literature. You can refer to your lecture notes, books, reference books. You will get which instruction takes which states, and I don't know whether they will contain the logical reason behind that, but in the books you will find the how they are defined and for which instruction how much teach states will be required. I told you this Gonker. If you refer to that book, you'll find for each instruction how many teach states are required. I don't know whether that will contain the details. In fact, I don't know how they come up with these numbers, but most certainly it will contain the details how much which instruction takes how much amount of delay. So you'll certainly find that. But regarding this reasoning behind it, I'm not sure about that, to be honest. But you please check that book. Maybe you'll find something there. So then we have question number 6. So how many T states are required to execute the following instruction? LXID 2589 requires how many T states? So it requires only 70 states. Option C. No, it requires 10 T states. Sorry, it requires 10 T states. It requires 10. LXID requires 10 T states. Then we have question number 7. It states that in the following 8085 assembly language program, so I'll repeat, in the following 8085 assembly language program, assume that carry flag is initially reset. So carry flag is 0. What is the content of accumulator after the execution of the program? So we need to find out the contents of the accumulator after the whole program has been executed. So what I have here is we'll have this instruction MVI. So move immediate A, contents of accumulator as 04 hex. So my A will be equal to 0, 0, 0, 0, 1, 0, 0. So this is my A. and my carry flag is 0. Then I have the condition RRC. So that is rotate accumulator right. Every bit position is shifted towards right. That is basically the divide by 2 operation. So everything will be shifted by 2 towards this right. So this will be 0, 0, 0, 0, 0, 0, 1, 0. So now my accumulator is 0 to hex. The contents of accumulator is 0 to hex. So first we just a second, someone wants to join. Yes, not in there. Six, six, six. So what I was discussing is I was discussing this thing. So first move immediate A with move the contents. So we need to contents of accumulator gets sorted by the 0, 4, and then we have the RRC, which is the rotate accumulator, right? So the each position gets shifted towards by one bit. So that is 0, 0, 0, 0, 0, 1, 0. Now the contents of accumulator are 0 to hex. Then we have move B comma A, that is move the contents of accumulator A, that is towards the B. So B gets loaded with 2. So here I will write B is equal to 0 to hex, and A will remain at 0 2. Then I have RLC. So now what RLC does is it will move the contents of the accumulator, shift it by 1 bit, push it towards the left. So everything will go towards left. Uh, my mouse is not actually working quite well today. So RLC, it will move towards left. So it was 2 earlier, now it will be 4. Then I have RLC again. So here my A became 4x. Now it is moving 1 again. So it's 1 0 0 0. So it is A equal to 8x. Now what is the operation? Operation is add B. So add B means adding contents of B to accumulator. So B was 0 2, that is 0 0 0 0 0 0 0 2. Sorry, I wrote it decimal 1 0, and 0 0 0 0. This was B, and this is A, C 1 0 0 0. So 8 plus 2 is simply 10. So you can just simply write A is equal to 0 0 0 0 1 0 1 0. So A is my 10 hex. A is my 0A hex. And this thing, my final instruction is RRC, moving the contents of register by 1. So it will be A will be 0 0 0 0 0 1 0 1. So this is 505x. So after the execution of this program, the contents of accumulator are 05x. So option E is the correct answer. Yeah, one of the students had already done it. Nice. Now we have the next question. So next question I would like you guys to do first, and then I'll show the solution. It states that what are the contents of accumulator after the program is executed? LXI B, that is it loads the BC register pair 0400, then loop where a decrement B, then move the contents of A, then ORA, basically the OR operation between B and A, then jump on non-zero to loop. So you need to find out the contents of accumulator uh, for for this. So it will take hardly 5 minutes. So I'll give you guys 5 minutes to do it, and then I'll just show the solution. So are you guys doing it? So in the earlier slide, I told that zero flag is a one. I think I messed up there. So zero flag is one. After arithmetic operation, result is zero. It is reset z equal to zero if it's a non-zero. So z equal to one if after arithmetic operations accumulator is zero zero. Z equal to zero if it's a non-zero. So have you guys done this question? I think it should not take this much time, but anyways, I'll just give a couple of minutes more. Anyone with the answer? So now let me just show the solution. So since it contains a loop, there will be many iterations. So I'll just divide it into table. So here I have this. So first instruction will be constant. So this is a one-time instruction. So LXI B. So this stores 400 hex. This stores register B as 04 and C as 00. But so this is your this thing. Then we have loop. So loops in from here I'll have iterations in. So this is my first iteration 1. So this is decrement B. So decrement B essentially reduces the value of register B by 1. So B was 04 hex, now it's 03 hex. Then move the contents of C to A. So C is 00, then A will be 00. So OR-AB, you know this instruction? This is basically OR operation between A and the register B. So A OR with B. So 03 OR with 00. So you have this property, right? In OR option, A OR with 0 is always A. So that implies it should be 03. Now jump on non-zero. Since the result is a non-zero, as you can see 03 hex, it goes back to this thing, right? Now iteration 2. So 03 hex now gets decremented by 1, so it will be 02 hex. The contents of C will be again moved to content to A, so A will be 00, A. Then OR of A OR with B. So 02 OR with 00 is 02. Then jump on non-zero is met, and we are right here in iteration 3. So here it's 02, so it's 01, right? So it's zero 03, 02. So A is 02, right? A is 02, and now B is decremented, so B will be 01. B will be 01 hex. So A is contents of A, C, that is 00. Now it's OR operation between A and B, so it's 01. Again, this condition is met. So we are now in iteration 4. Now decrement B. So B will be 00. A is 00. After OR operation, I'm getting 00. Now this condition is not met. So what are the contents of accumulator after everything is done? It's 00. So option D is right. So what we did here is decrement B 03, then move contents of C to A, then OR operation, so 03. Essentially, this OR operation is giving the results of contents of B only. And finally, this became 00, OR of 00 with 00 is 00. It became 00, condition was not met, and hence contents of accumulator are 00 after the whole thing is executed. So option D is the right answer. So is this clear? Okay, so now I have another question along these lines only. So yeah, yeah, right. Yes. So if you take, I have made this table. So iteration one, after decrement operation, B got 03 and A got 00, and then A was the result of OR operation, that was 03. In iteration through, it was a result of OR operation, that is 02. In third iteration, it was the result of OR operation, that is 01. And now I am going back to the decrement. Since contents of accumulator in third iteration are 01, so this satisfies the loop condition. It goes to the loop. Now B is 01, B got decremented by 1, that is 00, right? Now 00 is ORed with 00 because C is always 0, right? C is moved to A and 00 is ORed with B, that is 00. OR of 0 with 0 is 0. Now the contents of accumulator after OR operation are 0. So that condition is not met since it's not a non-zero. That's why it will not go into the loop again. And contents of accumulator will be the result of the operation, that is 00. Yeah, got it? Yeah, okay. Now, this question I would like you guys to do first. It's a very simple question. It states that what are the contents of the accumulator after the execution of the following program? So you are given this following program. What you need to do is again find out the contents of the accumulator. I'll just spell out the instructions here. So it's move A, so move A, then move B, then it's A and A. It's a mnemonic of AND operation between the register and the contents of the accumulator. Then it's XRAB, it's a XOR operation, XOR operation should I say rather, XOR operation between the register B and A. So, and A and A basically stores the result in the accumulator, and XOR A will also store the result in the accumulator. So can you find out the contents? It will not take more than 3-4 minutes, so I'll just wait for 3-4 minutes and you guys can come up with your answers and type it in the chat box. Hmm, but your answer was correct. So anyways, It's a request, please type your answers rather than. I guess I have told you the answer, but still, I'll wait for other participants. Yeah, option C is correct, as you already had told. But I guess you confused with the operation, but still your answer was anyways correct. But maybe the methodology was wrong there. So, anyways, yeah, a couple of students have given the answer. So let me just show the solution now. So here we have this instruction: move A 4E8. So A gets loaded with this 4E, right? So in binary we can write it like this: E is 14, so 1110. Then I have move B, so B gets loaded with 10 hex, so that is 0001 00000, right? Then you have A and A B, so it's a AND operation between B and A dot B, and the results are stored in the accumulator. So it's basically so it's 0 0 0 0 0 0 0. So after this, A became 00 hex. Then I have XOR of A, XOR of B, XOR A B. That is mnemonic for XOR operation between B and A. So it's A XOR B. So it's 0 0 0 0 0 0 0 0 XORed with 0 0 0 1 0 0 0 0. So this is an XOR operation, and this thing will be equal to, so 0 0 0 0 1 0. So this is 10 hex. So after these thing after this thing, the contents of accumulator are 10 hex. That is option C. Now we have this question 10. The accumulator contains 0 FB hex and B contains 12 hex. Rather, I should say 12 hex. What are the contents of A and B after the given instruction is executed? So we are given the contents of accumulator A, we are given the contents of accumulator B. We need to figure out what are the contents of the accumulator after the following instruction is executed, and the instruction basically is an OR operation. So basically, we are given this A, that is FB hex, and this thing is FB is 1111, and B is 11, so 8 plus 2 plus 1 1 1, right? And then I am given this B is 12 hex, so that is simply 0010, and then 00, sorry, 00110. So this is 12, yeah, this is 12 hex. Now I have to do A plus B, that is or operation. So this is 1101 So this is F, and this is 8 plus 2 is 10, 10 plus 1 is 11. This is FB, right? Yeah, FB. So A after operation became FB, and B will be the same as initial, that is 12 hex. So option B is the correct answer. A is equal to 0 FB hex and B is equal to 12 hex. Right? Yeah, some of the students have already done it. Nice. So now I have this question. It states that what are the contents of the accumulator after the following instructions are executed. So we are given with this following instruction, and we need to figure out what are the contents of the accumulator after these instructions are executed. So first of all, we have this A, move A 12. So A is 1 2 hex. There is 0 0 0 1 0 0 1 0. Then I have CPLA. So basically, this is a complement of A. CPL stands for complement of A. So all zeros are 1 now, and all ones would be 0. Then I have add, right? So I have this add A01 hex. So I have to add A with 01. So I am essentially adding 0 to 1 to accumulator. So it will be 1 plus 1 is 0, 1, 1, 1, 0, 1, 1, 1. So my contents of the accumulator are 1, 1, 0, 1, 1, 0. So it's 8 plus 4 is 12, 12 plus 2 is 14, 14 is basically EE. So my contents after the first I wrote A, then I took the complement, then I am adding 1 to the complement. So it is EEX. Because this is 14, 14 is represented by E in hexadecimal. So this EEX option B. Yeah, some of the students have done it. So okay, I think it was the previous question. There also option B was correct. So just a small question here. Can you tell me what is basically happening here? What is this entire operation doing? No, 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 no. Yeah, yeah, yeah. No, I'm not saying explain the operation. I'm just saying what is this operation, complete operation? Can you name it? Can you? Yeah, yeah. It's two's complement, right? Yeah, two's complement. Yeah, yeah. Basically, we are taking one's complement, then adding one to it. So essentially, it becomes a two's complement. Yeah. Then I have another question, which is question number 12. So, which of the following instruction is not an example of implied addressing mode? Option A CMA, option B ORIA, option C LDA 5689X, option D MVIB. So, the correct option to this question is option A. So basically, implied addressing mode means no operand is specified in the instruction. Data is itself present in the available instruction itself, like RLC, RRC, CMA, and all. No operand, basically, no operand is specified in the instruction. Data is itself present in the instruction. So option A is a correct answer. Now I would like you guys to do this question, and then I'll show the solution at the end. So, what are the contents of register B after the following instructions are executed? MVIB FFX, MVIC FFX, then INXB, that is the increment the contents of register pair, and what are the contents after the following instructions are executed. Yes, that was pretty obvious. So FFFF gets incremented by 1. All other by incrementing 1, all other bits gets to 0. So it will be 0 0. So this is FF, that is 1 1 1 1 1 1 1 1 1, and INXP basically increments the contents of register pair as one entity, and that means why when you increase this as by 1, so it will become 0 0 0 0 0 0 0 0. So option B is the right answer. Then I have question 14. Just it is a simple question, basically from the last week's last week and this week's transition question. So it states that consider the following VHDL code. What does it represent? So we have process begin clock 0, wait for 20 nanosecond, wait for clock 1, wait for 12 nanosecond, and process. So can you guys tell me what it is? Anyone? Okay, some of you have written. Okay, you corrected. Yeah, I was just expecting that. So, as you rightly pointed out, so this is basically a clock with on time of 12 nanoseconds. So, option B. So, one thing I wanted to point out, this is a never-ending cycle because nothing is specified in the sensitivity list here. So, it will produce a clock like this, where on time is 12 and off time is 20. Now, question number 15. Can you guys tell me how many T states are required to move to execute MOV, that is move AC instruction? Can you guys tell me how many? Yeah, it's nice. All of you have written the correct answer. That is option A. Next, what happens to the content of stack pointer after push instruction is executed? A. Contents of stack pointer decremented by 1. Contents of stack pointer decremented by 2. Contents of stack pointer incremented by 1. Contents of stack pointer incremented by 2. Anyone? Yeah. So, as rightly said by the student, so contents of stack pointer get decremented by 2. Now I have this question. I would like you guys to do it first and then I'll show the solution. So it states that the clock frequency of an 8085 microprocessor is 5 megahertz. If the time required to execute an instruction is 1.6 microseconds, then the number of T states needed for executing the instruction is. So you need to figure out the number of instructions. So I'll give you guys 3-4 minutes to do it, then I'll just show the solution. So you guys have done it. A couple of students have written their answers. So now let me just show the solution. So it states that the clock frequency of an 8085 microprocessor is 5 megahertz. If the time required to execute an instruction is 1.6 microseconds, then number of T states required for executing the instruction is. So basically, total execution time is basically Number of clock cycles required, that is number of T states. You can say the number of T states multiplied by the time period of the clock, of one clock, one pulse of clock. So you can say that T. And your F is equal to 5 megahertz. That implies your T is equal to 1 by 5 megahertz. That is 1 by 5 into 10 to the power 6. So total execution time is given as 1.6 microseconds is equal to T multiplied by N. So N is equal to 1 by 6 by T. So 1 by 6 microseconds. Don't forget the unit. So it's 1 by 6 into 10 to the power minus 6 seconds. So I'm missing somewhere 1.6 into 10 to the power minus 6 10 to the power minus 6, and your T is 1 by 2 is 0.2, 0.2 into 10 to the power minus 6. So T is basically 0.2 into 10 to the power minus 6. So this and this will go. So 1.6 divided by 0.2 is simply 8. So number of T states required is 8, as rightly pointed out by the students. So option D is the correct answer. Now I have this question. The following 5 instructions were executed on a 8085 microprocessor, that is MVIA 6. The contents of accumulator immediately after the execution of this instruction is basically after all the executions are executed. So you need to find out the contents of accumulator. So A is your 6 5 x, so that is 0 1 1 0 1, 5 is 0 1 0 1. Then B is 12 1 2 hex, sorry, it is 0 0 0 1 0 0 1 0. Then add B. So add B means add B to A. So it is an addition operation. So this thing will be 6 5 plus 1 2 is simply 7 7 hex. In short, you can write to 7 7 hex, that is 0 0 0 1 1 1 0 1 1 1. And then CMA, that is a complement operation. So it's 1 uh, 1 0 0 0 1 0 0 0. So it is 8 8 hex. Then I have this instruction ANI 68 hex. So ANI is just mnemonic for AND immediate. So the contents of accumulator get ANDed with this 68 hex. So 1 0 0 0 1 0 0 0 0 1 1 0. It is 1 0 0 0. So AND operation result will be 0 0 0 1 0 0 0 1. So sorry, 0, it will be 0. So it is 0 8 hex. So option A is the correct answer. Any doubts in here? Yeah, you guys have already done it. That's nice to see. So this was question number. This was question number 19. Yeah. Now we will do question number 20. So okay, this was question number 18. Now we will do question number 19. So I would like you guys to do this first. So what is the total delay produced by the given program? Assume 8085 operates with 5 megahertz clock. So you are going with this program and you need to find out the delay. Do it, then I'll just show the solution. I clearly remember this question. Now, while I was preparing my lecture, I didn't remember that time, but now I clearly remember this was the question in last year's assignment, and after the assignments were evaluated towards the end, I remember in live session number 12, one of the student she asked me that, can you please check this question? So two of the options were correct. It's quite strange. Both A and C are correct here. So option C is simply A. Check it. Am I right? Does that make sense? Yeah, you are correct. Yeah, even she had given it in microsecond. I remember. She told me that they had detected her marks. I told them I don't have control over that, but you can write to the team and they can correct. So both of them are correct. Right. Now I remember this. So all of you have done it. So now let me just show the solution. I don't care about the correct answers and all, but if if your concepts are clear, if you follow the right methodology, that's what matters to me. Obviously, marks matter at the end, but still, you are in the learning process. How you approach a problem, how you solve a particular problem, that should be your goal. The end product will always be great then. So I have this instruction LXI B. So this loads a register pair BC as 0, 1, 2, 3. That is 0, 1, 2, 3 hex. So this is simply 16. This is 16 into 2, that is 32, and 16 square, that is 256. 256 plus 3 plus 16 is 256 plus 3 plus 16 is 256 plus 3 plus 16. So 16 square is 256 plus 16 into 232 plus 3. So 291. So this is 291 in decimal. Then I have DCXP. So this DCXP basically reduces the contents of register pair by 1. Then I move contents of this to A to C, and then ORA B, and then jump on 0. Basically, this will execute, the loop will execute total time will be T inside the loop plus T outside the loop. T outside the loop will be 10. T inside the loop will be 291 multiplied by how many states it takes. 10 plus 4 is 14. 14 plus 4 is 18. 18 plus 6 is 24. 291 times, but it will be 70 for the last case, so minus 3. So this thing is equal to 6981 T states. You can do the maths, that's not an issue. And TOL is 10. So total T is basically 6981 plus 10, that is 6991. And your clock is 5 megahertz, that is zero point 0.2, that implies T is equal to zero point 0.2 microsecond. So your total delay will be equal to n multiplied by, this is n, let me just call it n multiplied by the time period. So this is 6991 multiplied by zero point 0.2, that is 1398.2 microseconds, or you can also write it as 1.398 milliseconds. So both option A and option B are correct. Now question 2 is, what is the content, accumuulator's content after the execution of following instructions? So instructions are MVI A55X, so that is 0 0 0 1 0 1 0 1 0 1 0 1. Then RLC, rotate accumulator, RLC or R, yeah, RLC. So it will move by one pushing towards the left. So it is 1 Z 1 1 0 1 0 1 0. Then again RLC, so it is 0 1010101. So RLC, RLC, then again RLC. So it's 10101010. So this is your A, this is your A. So the contents are AAX. So option B is the correct answer. Then what are the contents of BCA register pair after the following instruction is executed? LXI B, A B, CDX. Anyone? Anyone? What are the contents of BCA register pair? Yeah, option C is the correct answer. So let me just mark it. So LXI B basically wrote BCA register pair. B will be A B X and C will be CDX. So option C, B is called ABX, C is called CDX is the right answer. Then I have this question. I would like you guys to do first. Then I'll just show the solution. It states that what is the content of accumulator after the execution of the program. Assume 8085 flag register is initially reset. So we are given these instructions and we need to figure out what are the contents of the accumulator after the execution of following program. Are you guys doing it? Has anyone done it? Or are you guys still doing it? Just confirm that. I assume you guys are still doing it. So let me just wait for a couple of more minutes and then I'll show the solution. It takes time, slight time, not that much, but it takes. So one of the student has written an answer. Let's see whether that's a correct or not. So let me just show the solution. So first of all, we have this instruction MVI A F2X. So A will be 1 1 1 1 0 0 1 0. So this is your A. Then RRC means rotating through, that is shifting each bit by 1 towards the right. Each bit goes to the next bit towards the right. So it becomes 0 1 1 1 1 0 0 1. So that is 7 and 8% is 9, 7 9 hex. So A becomes 7 9 hex. Then we have move BA. So in the contents of accumulator get moved to B. So B becomes 7 9 and A is 7 9 as it is. Then we have this instruction RAL, that is rotate through accumulator left. So I have A. So this is rotate accumulator left through carry. So RAL. So I have 7 9 hex. So 0 1 1 1 1 0 0 1. So basically what it does, RAL, let's say I have my bits like this: D7, D6, D5, D4, D3, D2, D1, D0, and here I have carry. Shifting happens towards right, left, 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 and then D7 goes to carry, and carry, what was the carry earlier, will go to D0. So here initially carry was reset, so carry was here up to this point is still 0. So it will go to left by one position. So I'll just mark like this. So it will be 1 1 1 1. Then it will be 0 0 1 1 1 1. And it will be 0 0 1, and carry was 0. It will be like this only. So A is my F2. So A is F2 hex, right? After that is RAL again. So F2, it will be shifted. I'll write F2 here first. So it will shift like this, and carry is still here is 0. So it will shift towards left by 1. So A will be 1 1 1 0 0 1 0 1 0 0. So it is E and 4, but carry will now be equal to 1 because this thing moved into carry flag. So it's E4. So it's E4. Now I have add B. So A plus B needs to be done. So A is 1 1 1 0 0 1 0 0, and B is 7 9. So B is 7 9. So it's 0 1 1 1 1 0 0 1 So it is 1 0 1 1 1 1 plus 1 is 0, 1 plus 1 is 1, and 1 plus 1 is 0, and 1 will go to the carry. So because the result is greater than the n bit, so carry is 1. So it is 5. Accumulator is now 5, and this is 8 plus 4 is 12, 12 plus 1 is 13, 5D. If I am not mistaken, yeah, 5D. The answer to this result was 15D hex, but since the result was greater than the 8 bits, so 1 carry goes to 1. Now I have RAR, the final instruction on 5D on this thing. So RAR is basically rotate accumulator to carry. RAR is like this: D7, D6, D5, D4, D3, D2, D1, D0. Everything gets shifted to 1 towards the right. D0 goes to the carry, and the carrier goes to, and the carry that was earlier will go to D7. So everything goes to right. So it is everything goes to right. So first the carry will come here. Here everything goes right. So it is 0 1 1 1 0 1 0, and the carry was 1. So it's 1 0 1 0 1 1 1 0, and carry will again now will be 1 because of this. Carry is 1, and this is my final contents of the accumulator: 1 0 1 0, that is A, and this is 8 plus 4, 4 plus 2 is 14, so it's AE hex. So option A is correct. Let me just repeat this thing again. First, the accumulator is loaded with F2. I have written here as F2. Then A gets shifted to right by 1 bit push in RRC, so 1 bit shifting towards the right, so it becomes 7 9 hex. Then A is moved to B, contents of B are loaded with A, move operations began, so it's 7 9 hex. B is 7 9 hex. Then A is RAL, that is rotate left accumulator through carry. Basically, in rotate RAL operation, what it does, D7 bit goes to carry, and the carry goes to D0, and all other bits are shifted towards left left left. All that means D0 goes to D1, D1 goes to D2, D3 goes to D4, D4 goes to D5, D5 goes to D6, D6 goes to D7, D7 goes to carry, and whatever the carry was earlier will go to D0. Same happens here because earlier carry was 0, and the operation after this RAL becomes F2. Then again RAL is done on F2 and it becomes E4. Then E4 is added to 79 hex. So this result will give us the 15D as answer. Since the carry is there, so carry will be equal to 1. Now RAR is done. So in RAR, what is this? Each bit shifts to right. So that is D7 goes to D6, D5 goes to D4, so on up to D2 goes to D1, D1 goes to D0. D0 goes to the carry, and whatever there was the carry will go to D7. So this operation happens, and my final result is AE. So option A is my correct answer. Any doubts in here? If not, let's move forward to the next question. So, which of the following is not a general purpose register? Can anyone tell me which of the following is not a general purpose register? Which of the following is not a general purpose register? Anyone? You can use your microphones if you want. Yeah. So option D, accumulator. I was just expecting someone will say A, B, C, D. So it's a trick question. Fun question, you can say, like, which of the following flag is not available in 8085 microprocessor flag register? We have discussed it earlier. So can anyone tell me which of the following is not available in 8085 microprocessor flag register? Yeah, that's right. So that was all for today's live session. We discussed the questions related to 85 microprocessor. Next week, which is the last live session of what should I say, last live session of this course, digital circuits. We'll again be discussing questions related to microprocessors, some other types of questions we'll be discussing. That will be the last session, and that will be held on the same day as we usually meet, that is Sunday, 3 to 5 p.m. Uh, Hope to see you there. And other than that, if there are any queries, if there are any questions, do ask me. If in fact you get any queries or questions later on, you can always comment on the YouTube video. You have access to those videos. That was all for today's live session. Thank you guys for joining.